Okay, so the recording started. Today we focus on design of climate change adaptation actions, and this lecture is a bit overlapping with something that we already did and something that we will do in May. I will highlight the overlaps and I will either skip them or go through them very quickly. Let me open now the PowerPoint. This lecture changed a little bit yesterday. I added some figures which are still in Italian, but I think you can understand. In any case, I will change the writing in the figures, but you have to give me some time. And the PowerPoint doesn't include these figures that I recently added. It's not a problem because I will refer to the web page when the PowerPoint will get to this point. And it's not a problem for you because remember, for your studies, you should focus on the content of the web page, not the PowerPoint. Okay, the PowerPoint doesn't include everything in general. Okay, so what is this topic about? Here we are getting into the design of adaptation actions for climate change. We already discussed what is our approach, which is a risk-based approach. So we already know that in order to make the design of climate change adaptation action, we take this option of the risk-based approach, which implies an estimate of the probability of a given event, which we want to mitigate the impact of, probability, vulnerability, and exposure. And we discussed about estimation of probability extensively. And we also discussed about models for both studying climate change, so studying probabilities for the future. And we also discussed models for estimating the impact of climate change. These approaches allow us to estimate design variables, which means for our projects, for our adaptation projects. And the discussion that we did is very general so far. So we said probability of an event. We didn't specify a specific event. We said vulnerability and exposure, but we didn't, and we said impact models. We made some reference to, especially to the water cycle. Today we made a reference to the urban heat island, and a model was presented in order to estimate the heat island effect. But so far we didn't discuss specifically the actions, and which is something that I want to start today. And we didn't discuss how to prioritize these actions. So in case we are exposed to a risk of flood, and then we realize that there is a relevant risk that we want to mitigate, we may have several different options, like, for instance, structural measures in order to mitigate the risk of originated by the heat island effect. Today, we learned that we have several alternatives. So what is the alternative that is to be given the highest priority? Today, we saw an example where they proposed to identify priorities basing on the cost and basing on the effectiveness evaluated in some way. Okay. And for floods, for instance, an option may be structural measures like I build an embankment or I build a dam in order to store part of the flood water. Another option may be the so-called nature-based solutions. And today, this is a relevant discussion. So when we adapt to climate change, should we give priority to the so-called structural solutions, or should we give priority to the so-called nature-based solutions or green measures? And it is a topical issue. And you have probably have heard some discussion about that. There are some pros and cons for both of them. So at the end of the story, you have to decide what is the highest priority. And in order to aid, to support your decision, you may refer to the science called decision theory. which helps you to assign priorities. Today, we will not discuss about decision theory, only briefly, but only briefly just to set up the context. We will discuss decision theory in May. And today we discuss about these actions and how to give priorities by looking at their effect on mitigation. Decision theory is another thing. Basically, decision theory requires that you set up a criteria, the criteria we discussed today. And then once that you have a criteria, decision theory helps you to identify, basing on the criteria or several criteria, the best option. Okay, but let's focus on the discussion today. Design of climate change adaptation action. We already know what is the difference between climate change mitigation and climate change adaptation. We already discussed it. And it's important to know that any adaptation measure implies an impact. So we want to adapt to an impact caused by climate change, but any intervention that we make have side effects. We cannot identify a solution that is only positive. Okay, the side effect may be that the solution is not very efficient, or the side effect may be like the case of the solar panels that you see here, the loss of land. This is a problem of solar panels from several perspectives. It's not only a problem of visual appearance. You see on the left picture that indeed it's not a good visual what we get after the installation of solar panels. Also, wind farms have a relevant problem of visual appearance and the deterioration of the skyline of the landscape. Solar panels have also an impact in terms of drainage of rainwater, because of course the surface covered by solar panel is not permeable, and therefore there is a lot of research activity focusing on the effect on surface runoff, on drainage by the soil that is caused by solar panels. For wind farms, another side effect is the noise, which may seem something that is not disturbing, but indeed, if you got the experience of standing close to a wind turbine, you probably have realized that the noise is very relevant. And if you live there, you know, it's something that is maybe disturbing indeed. Now, what is climate change adaptation? We know it already, we know the definition. It's the process of adjusting to current or expected climate change and its effect. And what does it mean? It means to moderate or avoid bad consequences. And I want to put the accent on it, exploit opportunities. Climate change may deliver opportunities. Like any change, any environmental change, very often we modify the environment for the very reason that we want to take advantage from opportunities. So if you think about deforestation, like if you think at this region here, originally was covered by marshes and forests, okay? And we actually drained this area and cut the forests because humans wanted to gain in health, for instance, because, you know, very humid environment and are not healthy. But they also wanted to use the area for producing food. And this was an opportunity because we know how much is important food production today. So it is extremely relevant that we realize the opportunities delivered by climate change. And the opportunities may be, for instance, the urban heat island, may be that during the winter you have a warmer environment, which is less icy and so less risky and healthier. So the opportunities is something that we need to consider, study, and exploit. And we will see that decision theory is also aiming to help you in balancing between the risk and the opportunities, the potential damage and the potential benefit. It is not easy to make a balance of when you design a climate change adaptation action, to make a balance between what you gain and what you lose. And for this reason, we need decision theory. Adaptation may be incremental. This is something that is to be kept in mind. Incremental means that you can adjust it. And remember, when you deal with the environment and the climate, if you can adopt flexible solution, it's much better. And if you can adopt no-regret solutions, is much better. What is a no-regret solution? Is something that anyway doesn't lead to any regret, which means that in the worst case, you don't get any benefit, but you don't get any damage. And another important behavior characteristic is flexibility, as I said. Flexibility because you may need to adjust your intervention. And it is much better also in terms of usage of resources if we can move forward step by step. So let me focus on the figure that you see here that is taken from Wikipedia. So the scope of climate change adaptation and also mitigation is to increase resilience. This is another buzzword that you have heard several times. Resilience with respect to the considered impact. What is resilience? Is the ability to prepare and plan for, absorb, recover from, and more successfully adapt to adverse events. So this is a definition that you really need to learn. This may be a question on your quiz, because resilience is the target of any climate action, mitigation or adaptation, and especially adaptation, because of course it is perfectly fitting the definition of resilience. Now, let's focus on climate change adaptation. First of all, you see that in the upper row, with the pink background, you see a general classification of hazards, which are classified here as social hazards, like terrorism, technological hazards, such as industrial hazards, industrial risks, and natural hazards. Natural doesn't mean that they are not human-induced. Natural means that they are related to the environment. They are caused by environmental processes. This is a term that is indeed sometimes questioned, because many people say there is no natural hazards, because if you consider climate change, it's not natural. If you consider also earthquakes, it's it's natural, but can be also influenced by the human impact. It's more natural, but it's anyway influenced by the human impact. If you think of gas extractions, for instance, and also pandemics are classified as natural hazards. And among the natural hazards, there are the weather-related disasters, which are our main focus. Tropical cyclones, drought, wildfires, floods, severe storms, winter storms. These are influenced by climate change, as you know, in different ways. So it's important that for each of them, we identify a proper design variable. We identify a proper probability of future occurrence with the techniques that we know. So through probability theory and through models for estimating future climate change, maybe climate models, maybe regression, as we considered, or integration between the two. Okay, now let me make a premise to highlight the fundamental role of engineering here. It's a topical engineering problem. Climate change is not real engineering. It's more political science, social science, economics. There is some engineering also in mitigation of climate change. In the mitigation of climate change, there is also some engineering, because, for instance, you may have heard about geoengineering techniques, which means techniques borrowed from engineering to store CO2 in the underground or somewhere. But when we move to adaptation, adaptation is typically requires a project, a design project. Of course, it also requires an economic strategy, a political strategy, but it is a topic where the role of engineering is fundamental. So if engineering is not involved, I think this is a problem. And today it happens quite frequently because for several reasons, including the fact that engineering is considered to be a bit responsible, at least in part, of climate change. So there is some lack of confidence in the goodwill of engineers to support climate change mitigation and adaptation. But this is the reason why very often when you read reports about climate change mitigation and adaptation, in the reports, it's hard to find the solutions. You find a description of the problem, you find a global analysis of what is needed in terms of politics and economics, interaction. You find a lot of words on the overarching strategy, but when you look for solutions and how to design them from a technical point of view, you don't find much. So in terms of technical guidelines for climate change adaptation, there is still, I would say, nothing or close to nothing. And therefore, I think that involving engineering is essential, even if sometimes engineers may decide to take approaches that are not really liked by the interdisciplinary scientists, because in some cases, the engineers are very pragmatic and they prefer not to rely on models, but to rely on their perception of the problem, because the models are more uncertain. And therefore, the interaction is not easy, but it is extremely important. An example of a successful experiment is the Ridracoli Dam in the Emilia-Romagna region. And why did they decide to build this dam? Because with the increase of tourism on the coast of the Adriatic Sea, there was an increased use of water. And this water was traditionally taken by the underground. The main supply was from groundwater. What is the problem with groundwater? The problem with groundwater is that, first of all, we don't know it very much. So it is something that we don't see. It's hard to monitor. So basically, it's a big question mark, not a bit, it's a big question mark, the sustainability of the groundwater use. And also in the coastal areas, I don't want to go into the details, but it's a problem that I think it's interesting to mention to you. If you extract groundwater, fresh groundwater, which means not salted, you increase the intrusion of salt water from the sea that gets into the underground of the land and contaminates the fresh water. Because, in the underground, there are these two waters that are confronting each other, the fresh water that flows in the underground from the land to the sea, and the salt water that tries to intrude into the land because the sea is putting some pressure. And also there are sea storms which may increase this pressure. So in the underground, there is this confrontation. If you extract fresh water, of course, you reduce the energy of fresh water, and salt water may intrude. Once it's intruded, and once that the groundwater is contaminated, you can't use it anymore. So what did they realize in the vicinity of the sea? That the salinity of the tap water was increasing. And this was considered a big problem. How to solve the problem? Simply by reducing the extraction of groundwater. But for doing that, they needed other sources of fresh water. And therefore, they decided to build this dam in 1980, which is now fully working. It's also, it was a site that was very prone, very, very appropriate. It was an opportunity because it's a site that is in the mountains, is not inhabited, no houses were flooded. The lake is a good attraction for tourism, and Also, the sediment transport is very low. So after 40 years, the capacity of the reservoir is almost unchanged. And this is probably a structure that will last for a long time. So I think this was a good choice. And you know that dams are frequently criticized for their environmental impact. They have several environmental impacts. They are not much criticized for the risk that they originate. Of course, there is a risk downstream, but it is today we have all the means and the knowledge in order to reduce the risk to an acceptable level. The problem is the environmental impact. There are several impacts, and also, you know, it's a change. It's a change of the landscape, which is really impacting because it's something that you can see. In this case, the impact was reduced, but it is a change that is really impacting. So very often there are oppositions to the construction of dams. I would say that this dam is a good example. I am myself not in principle in favor of building new dams. I am more in favor of solutions that are more long-lasting, because these solutions may last for 100 years, 150, 200. But it's difficult to think of a dam that is going to last for 500 years. And I think I am more attracted by solutions that are final solutions. On the other hand, there is to say that we need solutions now, and we need effective solutions. So in some cases, dams are really needed. So there is no question that the development, our societal development in the Western world, was supported by the construction of dams. And in fact, also in the Eastern world, they are now taking advantage from this opportunity. I think this is a relevant example of climate change adaptation. So something related to water resources. But so today there is the full convincement. We realize that in order to get to the target of a successful adaptation, we need to involve not only the governments, not only the industrial sector, but we also need to involve the stakeholders. Involving the stakeholders, it's a bit of a problem, because the stakeholders are many, and very often the involvement of stakeholders generate discussions which are controversial, difficult to manage. And when you get involved in these very large discussions, there is the relevant risk that no action is taken. And our recent history is full of these examples of solutions that were already designed, already started to build, and then halted because of opposition of the public, which is fine, because I think that it's in a democratic approach requires, and also a successful approach requires, the confrontation with stakeholders. On the other hand, it's extremely important that we as engineers learn how to manage these discussions. Decision theory very often is nothing else than a useful tool to convince others of our decision. Very often, we know without applying decision theory what is the best solution, very often. And okay, we may be biased, but on the other hand, there are very few examples where decision theory led an engineer to change a solution or to opt for a different solution. There are plenty of examples of the use of decision theory to manage discussion with the stakeholders. And this is why decision theory is important. This is why I am dedicating some hours to decision theory. Decision theory is a topic that may be exciting, but may also be boring, like probability. I would say that it's a bit more exciting with respect to probability, but much similar. You will see that also it involves probability. The decision theory may be more exciting because it needs to be well understandable. So the stakeholders need to understand completely, with the max of transparency, how the decision is taken. Okay.
Prof?
Yeah.
Can you explain what stakeholders are, who
Yeah,
they are?
Yeah, okay. In Italian, stakeholders are portatori di interesse, just to give you the meaning in Italian. But stakeholders are, let's say, not only people, but any interested party in a decision. So maybe like an environmental organization, like for instance, if you decide for building a dam, the stakeholders are people who will use the water later, so they have an interest. And the stakeholders are also people who are not using water but are negatively impacted by the dam, like people who are submerged by the lake. Their houses are submerged, so they have an interest that they lose. And a stakeholder may be an environmental organization. A stakeholder may be a government. A government because if the government finances the dam, or the government is responsible for land management, then the government has an interest, has a role. I hope it's clear.
Okay, so not only the economical part, not
No.
only this. Okay.
No. It's not only economic. It's the stakeholder may also, as I said, be an environmental organization that is interested in keeping the environment in the pristine condition. And for instance, another relevant stakeholders for many of the climate change adaptation actions is the tourism associations, the local agency for the promotion of tourism. Okay, you may say that there is an economic interest, but it's very indirect. So it's not only an economic relationship, a direct economic relationship. You know that today you may identify some indirect economic relationship in almost everything that is related to environment. So environmental economics is indeed studying the development of the environment and environmental processes from an economic point of view. But the concept is the stakeholders are not only those who have a direct economic relationship. They are all the people and subjects in general that have an interest in that. Okay, good.
Okay, thank you.
Yeah. Okay, so let's try to give some more information on decision making, and then we will see, we will redirect our discussion on how to design climate change adaptation in practice. So a classical approach to decision making under climate change is the so-called top-down strategy. So the starting point is a future climate scenario, which is routed through an impact model. And then we obtain an estimate of future impact of climate change. And then through this model, we also generate the design variables. With design variables, I mean, it's a bad translation of variabili di progetto in Italian. Design variables are project variables. So the variables that we use to make a project. Okay. And so top down, climate scenario, impact model. Through the impact model, I understand the future impact of climate change, and through the same model, I generate the project variables. This is top-down. So what is the problem with the top-down approach? The top-down approach is propagation of uncertainties. So you start from a climate scenario which is uncertain, and then you apply an impact model which is uncertain. So uncertainty is inflated, and therefore the project variables are affected by uncertainty. It turns out, in our practical experience of this kind of approach, that very often we end up with project variables that cause oversizing, over-adaptation. Because climate models are inherently conservative, they are prudent, they usually predict disasters, which is fine for many reasons. In particular, for communication may be fine. On the other hand, for technical design, if we are overly conservative, it means that the cost of the intervention is overestimated, is inflated, and it implies that often no action is taken because we overestimated the cost, the required resources, and there are no resources for making adaptation. This is the problem of the top-down approach. I mean, being overly conservative in engineering is a problem. We have to avoid overestimation. Of course, we need safety factors. We need a conservative approach, but only to some extent. If we become over conservative, it is a problem. Now, recently, the scientific literature discussed a lot this problem. Because, as I said, if you look in general at actions that have been taken for climate change mitigation, climate change adaptation, we are not happy. So the scientific literature tried to devise an alternative approach. And the alternative approach refers to what I previously identified with the term no regret solutions. So let's try to identify solutions which can be taken, which can be implemented, and are no regret. Maybe these solutions don't solve completely the problem. So maybe that through these solutions, we don't get protected up to 2100, because climate change scenarios, usually we refer to 2100. So maybe these solutions are not final solutions, but on the other hand, they are doable, and they, in any case, help. If they are also flexible, this is perfect. A no-regret solution that is doable, doesn't solve the problem, but is flexible, so can be subsequently updated. This is perfect. This is the meaning of the bottom-up approach. What is called bottom-up approach? This is the target. And I will explain to you in a moment why bottom-up. Okay, and but the target is to avoid overestimation, to propose a solution that may be only temporary, but can be eventually updated and is doable. So why bottom-up? Because in order to identify a no-regret solution, the bottom-up approach focuses on the current problems, current vulnerabilities, current risks. We have a problem because otherwise we wouldn't be talking about climate change. I mean, if we wouldn't have floods, if we wouldn't have heat islands, if we wouldn't have hot waves or cold waves, we wouldn't care about climate change. We are not just caring about climate change because of model predictions. We care about climate change because we realize almost every day that there are problems which we attribute to climate change. Fine. So if we have problems, let's start from the problems, from what we need to solve these problems. So we start from the bottom, we start from people. We don't start from the top of the hierarchy, which is government, climate scenarios. We focus on people, we start from the grassroots. And then what is the purpose? To assess the local context in terms of vulnerability, what are the problems? And then, depending on the problems, we identify the candidate strategies. Okay, we didn't consider so far climate scenarios. We just identify strategies, which are no regret by definition, because they focus on current problems. And then we try to identify strategies that are flexible. Then, once strategies have been identified, we can consider climate scenarios. And the question is, to what extent these strategies also help in contrasting future climate change? And what solution may be possible to update these strategies in the future, or to update these strategies now while keeping the actions doable in order to get prepared to what the climate scenarios depict for the future. So you see that the uncertain part, which is climate scenario, comes later. We start from something that is less uncertain, because current problems, if I get flooded, there is no uncertainty after the event on that. Okay. So now, of course, the problem is not solved, because it is easy to say no regret solutions and flexible solutions. And this is what we usually find in the reports. The report of the IPCC, of several reports, which are very well informed, they say, okay, no regret solution, flexible strategies. But then what solutions are no regret, and how to analyze the current problems, how to identify the solutions to current problems. These are questions that are still open and are questions for the engineer. Okay, questions to be solved through decision theory, etc. This is a graph of the top-down approach and two types of bottom-up approaches, which now I will describe. But let's focus on the left columns for now. The left column starts from future scenarios, design variables, and vulnerability of system and strategies. Okay, now let's try, the scientific literature tried to go into the details, how to make a bottom-up approach, how to develop it. And here, and in the web page, I am presenting two strategies, which we will discuss later on, together with a third one. So now I am just passing over quickly. And the first strategy that I would like to mention to you is robust decision making, RDM. It's a bottom-up approach. And the second one is called decision scaling, and we will see why it's called decision scaling. But let's now focus on their workflow, which is similar. So basically, robust decision making, the term robust is referred to the solution that we design to our project. What does it mean, robust? It means that a solution is efficient, is a safe solution, which is a requirement for being a no regret. And therefore, the idea of the robust decision making is to identify strategies, so solutions, and then these strategies are evaluated against climate scenarios. So we identify the vulnerability of these strategies in the future, and then we pass to the elaboration and test of new strategies, which can be incremental in the future or new strategies at the present time. And then again, we evaluate them against scenarios. So the robust decision making focuses on solutions. The other method that I am mentioning here, which is in the right column, starts from vulnerabilities. So what is the problem? And then the future scenarios are used to estimate the future vulnerabilities. So now my problem is a heat wave. Okay, fine. I use the future scenario to see how the heat wave will develop in the future. There is the opportunity to get further information. further information which may be delivered by statistical analysis or by socioeconomic predictions on the evolution of the system, I mean, socioeconomic evolution of the community, for instance. And then basing on this assessment of current and future vulnerability, strategies are identified. I mean, the concept is the same. The concept is to focus first on the problem and its solution, and use the future scenarios as a verification. The difference in the workflow, which you may think it's a bit obscure, no? Why do we need these differences? What is the real difference in this workflow? It is essentially related to communication. So depending on the problem, depending on the discussion that you have to manage, it may be better to start from discussing the strategies, or it may be better to start by discussing the problems, the vulnerabilities. Very often you get into a discussion which is already informed, and the discussion is about a dam rather than a reduction of leakage in the pipe, in the use of water for irrigation and for drinking. So there are people who say that we need a dam. There are other people who say that by reducing the leakage, we can solve the problem. And therefore, the discussion is already focusing on strategies. In other discussion, you get into it, there is lack of water. Lack of water and no idea about the strategies. And therefore, it may be better to start from lack of water, future lack of water, and then the strategies come later. It depends on the communication. Keep in mind that it is not easy when you talk about climate change adaptation. It is not easy to set up a unique framework. So very often I have stakeholders who contact me and say, we need to reduce the damage caused by atmospheric events to buildings, to constructions, to buildings. And the last example was a stakeholder who said, I have several buildings in Italy. I need a strategy in order, because I have infiltration of water, I have overflowing of the pipes that deliver water from the roof to the sewer system, and several different damages. And I have big buildings, small buildings. I want a strategy. Okay, that's fine. And they asked, and then please, if you can produce a software. And they said, this is impossible. Why? It's impossible because any specific problem in climate change adaptation requires a different solution, depending on what? Depending on the type of risk. In this case, it was weather, it was precipitation, rainfall. Okay, that's fine. But depending on the extension of the building, depending on the availability of climate scenarios for the region of interest, depending on the availability of historical data for the region of interest, I need to estimate the new project variables with a different technique. I cannot, prepare a software because if I have historical data, I need to use also this information. If I don't have historical data, I have to search for other information. And depending on the extension of the building, also the project variable is different. If it's a small house, I have to look for changes in rainfall that lasts like 20 seconds. If it's a huge extension of a building, I have to look for longer rainfall. And climate change is not the same for rainfall of 20 seconds and rainfall of half an hour. It's different. So it's impossible really to look at, and also the scenarios are different. So it's really impossible to establish a formalized procedure at our state of knowledge. It's not like sizing a building where we have a software that once that you put into the software, the design variables, then the software does everything. Here it's not possible. Okay. Let's forget about future climate scenarios. We already discussed it. We said that we have climate models. We didn't focus on climate models, but I said that you can find the data from climate models on the web. It's not easy, I said, download them. It's not easy, but this in principle is not a problem. And also we know that we can use regression, we can use statistical analysis to project into the future the trends that we observed into the past. I am also skipping, this is a nice picture, I think, about tipping points, and which highlights once again the uncertainty in future predictions. So, I mean, when we reach a critical threshold, this is typical of environmental processes. There might be tipping points, we discussed them, that once reached may cause the system to evolve in an unpredictable way. So maybe that it's we can predict the first part of this graph until the vertical dashed white line. The first part with a regression line can be predicted. But a tipping point means that after the tipping point is crossed, you cannot make a prediction. So this is to emphasize uncertainty, but we already know it. Tipping point, we already discussed it, so I am skipping. Okay. Also, this one, it's cannot, I mean, it's already discussed, so I'm skipping it. And also, now let me recall a little bit our approach, because what I want to do now is to refer to the risk-based adaptation design and analyze how the risk-based adaptation design can be used to identify priority for solutions. So far we discussed the formula that you see in the bottom of the slide. Regarding probability, we discussed extensively about probability. We didn't discuss at all about vulnerability and extension. We defined them, but we said, let's, if you remember, I said a couple of months ago, I said, let's focus on probability, and probability, which means a return period of the event. And I said, let's assume that vulnerability and exposure are constant. So once that the event happens, no matter the intensity of the event, vulnerability and exposure are constant, which is not reasonable. And I said, if you remember, I will relax these assumptions later on. It's not reasonable to assume that they are constant. If you get a hot wave, and the hot wave is plus 4 degrees with respect to the average, you may have a vulnerability against it, which is reduced, because 4 degrees, if you have a good cooling system in the houses, you may reduce the impact. So vulnerability may be lower. So in the equation, you may get into a vulnerability that is close to zero, the risk is low. But if the hot wave is plus 15 degrees, the cooling system doesn't work anymore, doesn't protect you anymore. So in this case, vulnerability would increase, and then the risk would increase. So it's not reasonable to assume that vulnerability is independent of the intensity of the event. Vulnerability, if the intensity of the event, and therefore the return period, I hope you can follow me. Intensity of the event means that the event is less frequent. I mean, a hot wave of plus 4 may be quite frequent. A hot wave of plus 15 is something that is really exceptional, doesn't occur frequently, and therefore the return period is much higher. So vulnerability actually depends on the intensity of the event, and therefore depends on its return period, which is related to probability. So this is a complication, because in this equation here, I am introducing a relationship between V and P. And the same I can do for exposure. Exposure, it's not reasonable to assume that it's independent of the intensity of the event. So if I get a hot wave of 4+4, the damage, even in absence of, even with the vulnerability 1, I get a damage, okay? But the damage is not much relevant. If I get a hot wave of +15, the damage is much higher. More people die or more people get sick, and therefore the structure and the goods also deteriorate, the vegetation deteriorates more. So even exposure depends on the intensity of the event, depends on probability. So I am introducing some links between probability, vulnerability, and exposure. And now this is the purpose of this lecture, to discuss about this relationship. This is the main focus, okay? And this is the news. Let's make the break now, and then we discuss this figure, which I leave on the screen, so you can start brainstorming on it if you want. I just want to say one thing. This is a graphical representation that I elaborated, so feel free to criticize. You will not find anything related to this on books or the web, but my web pages and my presentations. So basically, the idea here was to provide a graphical introduction to the problem, which may also be useful for communication. And so the idea here is to, given that there is a relationship between probability, vulnerability, and exposure, here the idea is to put probability or intensity of the event or return period as an independent variable and study on the vertical axis vulnerability, exposure, and risk, where risk is derived as the product of probability, vulnerability, and exposure. Keep in mind that as the intensity of the event increases, the probability that we have to consider there is the probability of exceedance, which is tending to 0 as the intensity increases. After this introduction, we can make our break. Do we have any question?
Could you repeat shortly the difference between mitigation and adaptation?
Yeah, okay. So let me just go back to here. It is something that we discussed already in the, I think, but I'm not really sure if I dedicated actions and attention to it. So just one second. Okay, let's focus here. Climate change mitigation aims to reduce climate change. So a typical mitigation action is a reduction of CO2 emissions. And adaptation means to accept climate change and minimize, to take action to minimize its adverse consequences. So in the first case, the spatial scale is global, because if you want to mitigate climate change, reduction of emissions has to be organized at the global level. In the second case, the spatial scale is local, because adaptation is a local intervention, like building a dam, building a wind farm, etc. And in terms of time scale, mitigation is expected to produce effects in the long term, because climate has a long inertia. Adaptation is expected to produce immediate effects. Is it clear?
Yes, thank you. I wanted to be sure.
Yeah, okay. In the web page, there is a link on the Wikipedia page for climate change mitigation and climate change adaptation. It is very well done. Other questions? Okay, let's close camera and micro for 15 minutes. I apologize, I am a bit late. Okay, so let's start again from this figure. And let's try to understand how it should be interpreted. So, as I said, there is in the horizontal axis the intensity of the event, which is treated as an independent variable. Of course, the intensity of the event is actually not independent. It is influenced by climate change. But let's treat, for the purpose of this graphical representation, let's treat the intensity as an independent variable. Now, let's focus for now on the vulnerability curve. So, and let's try to understand whether the graph reflects what I anticipated. So, for intensity of the event increasing, vulnerability may be 0 up to a given threshold. Because, just 1 second, I think I have to admit a student. No. Okay. As I said, vulnerability may be 0 up to a certain threshold, because we may have some actions already in place which basically annihilate, cancel the negative effects of the event. Like, for instance, if my event, considered event, is an heat wave, I may have a cooling system that up to a threshold of +4 completely allows me to cancel the impact, to eliminate the impact of the heat wave, which means vulnerability 0 up to a certain threshold. Of course, this is case study dependent. What I am discussing now, the fact that vulnerability is 0 up to a certain threshold, depends on the case study. So you have to make a vulnerability assessment with engineering methods to understand how actually the red curve behaves. But let's suppose that up to a certain threshold, vulnerability is 0. And then it is reasonable to assume that after that threshold, vulnerability increases and reaches the value of 1 to a certain intensity of the event. Okay, so vulnerability 0 and then increasing with different pattern depending on the case study up to the value of 1. Now you don't see on the vertical axis any scale, any value, because otherwise I would have complicated the figure, because I should adopt different scales. Now, let's talk about exposure. Exposure is expressed in monetary terms, so another scale with respect to vulnerability. Now, exposure, in the same way, can be considered to be 0 up to a certain threshold, different with respect to the threshold of 0 vulnerability, and then increase up to a max value which corresponds to a given intensity of the event. A max value because we can assume that there is an upper value to the economic damage that is caused by an heat wave or a flood or whatever event I consider. So let's suppose that exposure has the shape of this blue curve. The red curve and the blue curve have in common one feature. And the feature is that they are always increasing. They cannot decrease after a certain value of the intensity of the event. They are not decreasing, let's say. Okay, they are not decreasing curves for increasing intensity of the event. Now, what about risk? Risk is given by the product of vulnerability, exposure, and probability, which is derived, it's depending on the intensity of the event. Increasing intensity, decreasing probability, because we have to think about the probability that an event of high intensity occurs. It's low. So the product of the three may reach a max. Risk is a curve that can be decreasing. being the product of two quantities that are not monotonically not decreasing, and one quantity which is constantly decreasing, probability of the high intensity event, then the product may reach a maximum, depending on the pattern of exposure, vulnerability, and then probability. So we may identify an intensity of the event which corresponds to the maximum risk. And then this is, we may assign high priority to protection against this event. Or we may use this representation to study how to combine adaptation actions to decrease risk over the whole extent of probabilities, event intensities. Because this graph can be used in order to visualize how vulnerability changes after an intervention, after an action, how vulnerability changes if I install a cooling system. And therefore, here I can visualize a new curve and then see the effect over the risk. And then I can decide whether I want to focus on the maximum risk or whether I want to focus on the whole spectrum of risk. Keep in mind that you may also want to focus on the extreme value of the risk, because maybe that even if a very high intensity event is not probable, is not likely, and therefore cannot be considered very risky, but you may be interested in specific situation in getting protected against an event that may occur maybe once in 1,000 years, but you want to absolutely get protected against it. So, for instance, with dams, given that the potential exposure is very large for high intensity events, for dams, we usually want to get protected against events that have a retro period of 1,000 years. So in some cases, you may want to focus on the final part of this curve, even if the risk, the corresponding risk is low. But it's low because there is a low probability. But in case the event happens, the damage is massive, is huge. So maybe that in this case, you want to be protected against the huge impact rather than the highest risk. So you have to understand what is the difference between the risk, which takes into account that probability may be very low, and the actual damage that you experience if an event happens. Okay, now the question is, how different actions change the shape of these curves? And then just let me see. Okay, here the slide explains what I already commented with my words. And okay, very good. So just 1 second. According to the bottom-up approach, let me comment on this slide. Adaptation design may be articulated in 2 phases. In a first phase, we assess the effectiveness in terms of vulnerability and exposure of the adaptation solution by referring to the what I call here PIV curves. Why PIVs is probability, exposure, vulnerability, risk. Okay. And in the second phase, we may analyze the impact of climate change on probability. Because, let me go back here. What I said is, I'm not considering in this graph the impact of climate change. I said, let me assume that probability is an independent variable. Actually, it is not independent, it is affected by climate change, but I can assume that is independent here. And then I can study the effectiveness of solution with respect to the current situation. Bottom up means current situation. And this is what I do in the first phase that I mentioned. I refer to the current problems, current probabilities, and then I estimate the effectiveness of the different adaptation solution. In a second phase, I consider the impact of climate change, which means that I change the horizontal axis. I make it dependent, and then, of course, the resulting curves change. So this is, according to the bottom-up approach, I first consider probabilities fixed, and then I consider the effect of climate change. And this is what is written in this slide here. Okay, now let me focus on the web page because, as I said, I added a couple of figures, and I want to show you. And the figures that I added, it's first of all here. Now, first, excuse me for the Italian. As I said, using the Italians is a big negative connotation. I will translate it, but you have to give me some time. Here I am focusing only the vulnerability and exposure curves, and I am displaying the retro period instead of the intensity of the event. And here you see that I also put some numbers, but it doesn't change anything because, as I said, the intensity is related to probability, which is related to the retro period. And the higher the retro period, the higher the intensity of the event. So it doesn't change anything. First of all, here, yeah, there is a question.
But is it a linear correlation between the return period and the intensity, or because I think you did that in R?
It depends on the probability function. So it's okay. It's not linear.
So it would change the shape of the.
Yeah, of course, yes. Yeah, it could change the shape of the curves. The question was, is it linear, the relationship between return period and intensity of the event? No, because it's regulated by the probability distribution function, which is nonlinear. So it is then if we change the scale of the horizontal axis, also the shape of the curves changes, but of course the association between the intensity of the event, vulnerability, and exposure doesn't change. It changes the graphical shape of the curves, yes. And okay, here, what the purpose of this figure is just to display that we may, through a proper assessment, identify uncertainty bands in gray here for vulnerability and exposure. And the uncertainty bands are not easy to be estimated. Also here you see that the width of the band is assumed to be more or less constant. It is usually not the case. It is not easy to estimate these uncertainty bands. Why? Because in terms of vulnerability, usually you have an impact model which gives you the assessment of vulnerability. Like for floods, it's an hydrological model. For the heat island effect is the model that was presented today. And the model has an uncertainty. And therefore, but estimating this model uncertainty is not easy. It depends on the model. It depends on the data that you have available to apply the model. And it's not easy. And the scientific literature is dedicating a lot of attention on it. There are some simple procedures, like, for instance, ensemble simulation. Climate models use ensemble simulation to estimate uncertainty. But I mean, it's an issue that it's still in the realm of the scientific activities. And also for exposure, you usually have a socioeconomic model to relate the exposure to the intensity of the event or return period. The socioeconomic model has uncertainty. Again, not easy to be estimated. And when it comes to future predictions, so in the second phase, when you analyze the effect of climate change, you also have to use a socioeconomic development model to estimate the future development of the socioeconomic setting. And these future predictions they are subjected to the uncertainty of the financial market, of all the uncertainties related to the socioeconomic and political setting at the international level. In some cases, maybe not really international. In some cases, you may have a simplified situation where you just have to make a prediction of the socioeconomic development of a municipality. Still, the uncertainty is not easily predictable, because even for small municipalities, the financial market is driving the future socioeconomic development in the current days, and the prediction of the financial market, as you see, it's not easy. But in any case, let's take into account the opportunity of estimating also uncertainty. Now, let me move to the next one, which focuses on solutions. And here, there is an hypothesis of how structural interventions may modify the vulnerability and exposure curves. Now, let me try to explain. When you realize you put in place a structural intervention, there is one important thing that you have to consider. A structural intervention has a range of efficiency, a range within which it's operative, it's functional. And usually the structural intervention is characterized by an upper limit of this range. Like, for instance, if you put a cooling system in place to contrast an heat wave, of course, you have an upper limit after which the cooling system is not protecting you anymore. And therefore, this is a first example. For the example of a dam for flood defense, it's the same thing. The dam reduces the impact of a flood by storing water, by keeping some of the water upstream. But when the dam is full, then there is no possibility to make any additional storage anymore, which means that all the inflow into the dam goes after the dam, which means vulnerability zero, vulnerability 1, sorry. From that point forward, the vulnerability is 1. And there is another problem with the dam, that vulnerability may be even amplified if the full capacity of the dam is reached. Because when people are close to full capacity, they need to react to avoid overspilling, and they release water from the dam. And therefore, there is the summation of the water that is released for safety plus the inflow into the dam, which means that the downstream flow may be even magnified. This is this happened, and it means that vulnerability may be even increased. If it was lower than 1 without the dam, may reach the value of 1 for high intensity of the event after the limit of functioning of the dam. What about, is it clear? So you reduce vulnerability within a range. Beyond that range, vulnerability may not be reduced or may be even amplified. Okay. What about exposure? There is an interesting consideration to be made about exposure. There were several studies that demonstrated that exposure may be increased if a structural intervention is realized. Why? Because people feel safer. There is a feeling of security that is given by the structural intervention, and they invest more money in their socioeconomic development, which means that they increase the values, the value of the goods that are exposed to the flood. And this may increase exposure. This is what is called by the international literature, by referring to floods, the Levy effect. The Levy effect is meant to indicate an increase of exposure of the land due to the feeling of security given by a levee. But actually, if the levee is overtopped, because a levee is a classical example of a structural intervention that has a limit of a limiting range of efficiency. If it is overtopped, what happens is that the levee collapses usually, and then you have an increase of vulnerability and an increase of exposure due to the levee effect. By the way, the levee effect was introduced recently by the international literature, but it was already known in Italy about 100 years ago. After the Second World War, people realized, after building several structural interventions, that the exposure associated to floods was increasing because people felt more secure. So this is a possibility. Of course, how the pattern changes depends on the specific case study, and the definition of these curves, both in the pristine situation and in the situation after the structural intervention. The definition of the pattern of these curves is your task, is the task of an engineer through impact models, usually, as I said. Okay, now next one, because this refers to structural intervention. And what about non-structural interventions? Let's focus on this. Non-structural intervention usually don't change exposure because people don't feel more secure with non-structural intervention. With nature-based solutions, with green solutions, people are less convinced of their effectiveness, and therefore usually the exposure doesn't increase. Vulnerability is indeed decreased, but in the usual experience, in most of the cases, the range of decrease of vulnerability is shifted on the left with respect to the structural intervention. The structural interventions usually are sized for events of higher intensity. Nature-based solutions usually are effective with low intensity events. Nature-based solutions are like green roof, increasing vegetation, etc. They are effective with low intensity events, but when the intensity of the event increases, then they become less effective. And of course, once again, the pattern depends on the specific case study, but you can see the difference, which allows us also to highlight that these solutions usually, which are discussed like they are interchangeable, actually they are not interchangeable. They usually are solutions that have different behaviors and different efficiency in terms of reducing vulnerability. And therefore, they shouldn't be discussed like alternatives, but they should be discussed as solutions to be combined because the most of the effectiveness is reached if you use a portfolio of solutions. Okay, now next figure. So what is the result in terms of risk? If I combine the two, no, here is still vulnerability and exposure. If I combine the two measures, you see that probably I obtain an integration of effects, and I obtain a larger range of effectiveness. And then here I also highlight that what is the model that you should use to estimate these changes. So hydrologic model if we are considering a dam, heat model if we are considering heat waves, and a socioeconomic model if I want to decipher the changes in exposure. I am still not saying how to design. We are still talking about strategies, and this is what you may find still in some reports: integration of portfolio of solutions. We are still not discussing how to design them. Okay, now Let's move forward with, and probably I can go back to the PowerPoint. Give me 1 second. Okay. Okay, now let's transition to design. So, and let me see if the list of measures, yeah. So, some preliminary considerations, which I am reading here. The effect of climate change vary by region. We know this. We really discussed this. We don't need to discuss it again. The effect of climate change may vary across demographic groups. So when we talk about exposure, and let's take into account that you know, the effect of climate change, the effect of crisis in general, are more impacting with respect to the categories which have less resources. So this is something to be taken into account, especially when we want to make consideration at the international levels. So when we talk about, I make an example, climate change mitigation, and we talk about policies for climate change mitigation, reduction of CO2 emissions, very often we propose policies that are not sustainable if for the population with limited resources. And this is something to be taken into account because all of these solutions have a social cost, and this social cost should be distributed in an equitable way. Equitable means that proportionally to the resources of the categories of people, which is something that is not easy because it involves political considerations. We already talked about the opportunities of climate change, so let's keep a focus on these opportunities, and when we will discuss decision theory, we will make a special focus on it. The effect of climate change must be considered in the context of multiple stressors and factors, and of course, we already discussed this. Adaptation comes at a cost, fine, we already discussed. Adaptive responses vary in effectiveness as demonstrated by current efforts to cope with climate variability. Yeah, one consideration which is important. When we make a bottom-up approach, when we make an assessment of current vulnerabilities, this is part of our usual and traditional approach to engineering and our traditional approach to natural hazards. So the moral of the story, and to go into the technical details, is that assessing current vulnerabilities means to use our traditional engineering procedures like probability estimation, the procedures that you learn during your studies in order to make this current assessment. So it is not true that under climate change we need new methods. It is simply not true. And it is not true that traditional methods under climate change are no more valid. So you may listen some people saying probabilities cannot be used in the presence of climate change. Traditional methods of estimating probabilities cannot be used, or the return period is an obsolete concept, which means probability is an obsolete concept. People say this because climate change indeed means that the past is not representative of the future, and therefore estimating probabilities based on our knowledge of the past may lead to erroneous conclusions. This is true. On the other hand, it's not true that these are obsolete concepts. We simply have to start from traditional methods and then in the second phase account for climate change. So the traditional engineering methods are still valid. And this is something that it's an important premise. Okay, and then maladaptation is to be avoided because maladaptation may be even worse than absence of adaptation. So this is something to be considered. And let's take into account that many opportunities for adaptation makes sense whether climate change will happen or not, because we start from the assessment of current vulnerabilities. And therefore, no regret solutions means that whatever it happens into the future, we have to avoid maladaptation, and provided that we avoid maladaptation, we are reasonably sure that the solutions will anyway be appropriate. Okay, now adaptation actions. Let's make a provisional and an incomplete list. They can be grouped into three categories: structural adaptation and physical adaptation, social adaptation, education, institutional adaptation. Here, in structural and physical adaptation, I include both what I called earlier structural solution, which now I should better explain. They mean hard engineering solutions, but structural and physical adaptation also include what I called earlier nature-based solutions, structural and physical adaptation. Okay, and you see between parentheses, this can be grouped into engineering and built environment, technological, ecosystem-based services. Ecosystem services are a synonym of nature-based solutions. But it is also important to consider, even if it's not in the domain of engineering, social adaptation. Social adaptation is extremely important. Education. And think about floods, for instance. Educate people to cope with floods as we educate people to cope with earthquakes. So with an earthquakes, everybody of us knows what to do, because basically we are told it. For floods, only a few people only know what to do if you get flooded. And there is indeed room for opportunities in social adaptation and also institutional adaptation, because of course laws, economic policies are extremely important. So structural and physical adaptation include flood and drought adaptation, agricultural adaptation, energy production adaptation, and many others. Social adaptation includes enhancing adaptive capacity, reducing poverty, etc. And also insurances. This is an extremely important item. So there are more and more contexts where people choose to adapt to climate change by stipulating insurances, which is indeed a good option. And then there is the institutional adaptation, which includes effective policies and development of adaptation plans. So examples of adaptation actions: installing protective and resilient technologies and materials in properties that are prone to flooding. And this is focusing on adaptation to flood and droughts, so adaptations to risks related to the water cycle, but I will make additional example. One additional example of adaptation is what we saw this morning: green roofs, urban forestry, etc. So changing to heat tolerant tree varieties. This is indeed again very relevant also for agriculture. So we should wonder whether there are opportunities with the warmer weather in agriculture. So we should wonder whether we should take advantage of these opportunities by changing our development model. So if we have predictions that of less water available for food production, for irrigation in the future, maybe that we need to consider shifting the agricultural production to less water requiring crops. And it is not easy. It is not easy because there is also the financial market driving these options, these choices by the farmers, and the financial market is indeed very relevant. So if we want to support a new development plan, probably we need resources to support the farmers to adopt, to follow the new development plan. Rainwater storage to deal with urban flooding and with water for irrigation. Changing to water permeable pavements, and we discussed it in the morning, adding water buffering vegetation, because as it was mentioned in the presentation, if we use green roofs, urban forestry, we may get several different benefits. We reduce the heat island effect, but we also reduce the flow in the sewer system. And reducing paved areas to deal with rainwater and heat, adding green roofs, okay, it's here. Requiring waterfront properties to have higher foundations in order to avoid that the foundations are eroded. Raising pumps at wastewater treatment plants, and surveying local vulnerabilities, raising public awareness, and making climate change specific planning tools like future flood maps. Incentivizing lighter colored roof to reduce the heat island effect, as we discussed, buying out homeowners in flood-prone areas. This is something that is frequently considered and difficult because we need resources. And raising street level to prevent flooding. This is used in some coastal regions. Okay, some conclusion to this first introduction. Design of adaptation action is a typical task of engineering, and traditional engineering practices are still valid. And a comprehensive assessment of uncertainty, it's not easy. And here it's explained in more details. So now we still have to understand how to make the design, how to choose between different alternatives, and this will be discussed when we talk about decision theory. I think for today we can close now, and I just want to say, for those of you, I think very few, who may be attending the other course that I'm teaching today in the afternoon, I will deliver a similar lecture, so that you know. Questions? Okay, thank you very much.